All right, well, hey, welcome to week 7. We are now in the second half of this class, by the way, home stretch. We're halfway there. Um, I hope you guys all had a good, long, extended weekend, although it feels like we haven't done calculus in forever, and probably that is the case for many of you. It's been a week. So my plan today is to continue talking about some physics examples. Specifically, we're going to be looking at center of mass. I gave you just a real quick preview with a couple of point masses. I'll refresh your memory about that, and then we'll go to more extended objects. So that's my goal today. If we still have time after that, we'll see how things are going. Then we'll talk a little bit more about logs and exponents. But before I take over and just start doing that, I want to open it up to you guys as always. Any homework questions or anything else that you want to talk about before we get going? All right, thanks, Alexi, from 2.5, number 23. I'll put that on the list. All right, so then Adam, so 9 to 12 or so. Okay, they all seem the same. So if I pick something like that or one of those.
Yeah, it makes, it seems like there's like a height missing. There's not enough dimension to do the question, I feel like, so.
Okay.
Yeah.
Yep. We can definitely take a peek at those. And then Chase just threw on 20 through 22. Is that kind of the same deal, Chase, where they're all kind of similar? You just want to see one of them? Or is it they're all, okay, yeah, okay. Put that on the list. All right. Then, and then number 17, Susanna. Okay, so I don't know if we're going to do all of these, but we'll at least talk about getting them all set up and the process. So I've got 23, 17, one of them from 9 to 12, and one of them from 20 to 22. All right, so 20 and 21 are similar, but 22 is different. Okay, well, we'll do a general overview. But like I said, that's going to be a little bit too much for us to do all of them. But let's go take a look. All right, so hopefully you can all see my screen here, physical applications. So let's jump down first for the 9 through 12. I will randomly pick 11. Oh yeah, which just reminded me on that exam question, remember the sign when I had you integrate from 0 to 11? I chose 11 on purpose because, I mean, everything goes to 11, right? It's one more than 10. That's a Spinal Tap reference, never mind. All right, so let's look at number 11. Like it's kind of early here. I'm a little punchy still. You guys realize Hawaii is 2 hours earlier? So when we start class, it's actually 6:30 in the morning. I know, sad story, right? Anyway. So let's look at this one. We're going to find the mass of a two-dimensional object, an oversized hockey puck of radius 10 inches with density function rho of x equals 5 plus 3 cosine pi x. All right. So is this good for the number 9 through 12? I think that was Adam who asked. Is this a good enough one?
Yep.
Okay. All right. So let me first write down my density, and then we've got radius 10. All right. So I'm going to start as I always do, which is drawing a picture. So let me go to the whiteboard real quick. Clear all that stuff. All right, so we've got hockey puck of radius 10. Looks something like that. And we want to find its mass if we know that the density is given by 5 plus 3 cosine of pi x. All right. So let's think about this one. If we want to find mass, what do? What's the general process?
Density times volume.
Okay, right. So it's density times volume, or in this case, it's density times area, because they tell us it's a two-dimensional object. So there's a hockey puck that's like, not even paper thin, but it's density times area, which means we're going to integrate, right? We're going to integrate rho, so density times, and in this case, area. Okay, so let's think about how we're going to do this then. The density depends on x, so we really need to think about what is the area for a given x. So that'll be our little slice. So if we want to get that area, that's going to be its height times its width. The width is going to be a dx, and then we need to get its height. Well, the height changes depending upon where we are on the circle, which would be really helpful if we had, say, the equation of said circle. So let's get that real quick. The circle, since it was radius 10, we know that its equation is x squared plus y squared equals 100. And if we solve that for y, it's the square root of 100 minus x squared. And that square root of 100 minus x squared is just this piece. Right? That's the y coordinate for that upper half. So if I want the height, what do I have to do with that?
Multiply it by 2.
Yeah, double it. So we'll have 2 square roots of 100 minus x squared. All right, so now we're ready to put this all in. So let's get our integral set up here. So we're going to integrate, and we're going to go from minus 10 to 10, because those are the extremes on this thing, since it's a circle of radius 10. We're going to get its density, 5 plus 3 cosine of pi x. And we're going to multiply that by the area. So 2 square root of 100 minus x squared dx. So there is the setup for this integral. In terms of actually doing that integral, it's going to be pretty gnarly. I would actually enlist the help of technology at this point. Just fired in my TI-89. And I will tell you this with applications, because when we were going over the exam, I was like, hey, show me your steps, show me your steps. When we're talking applications, what I'm looking for is, did you get it set up? Because that's where the work is, right? It's getting it set up. The integral after that, that's fine if you want to make use of technology. Anyway, so is that at least good enough for the setup?
Yeah, I think so. I guess I just, for one reason, being 2 dimensions, I wouldn't think you would have any volume at all, but it makes sense considering just area.
Yeah, well, and you're right. It would not have volume if we were actually given a density per volume. Then this would be 0. The reason they didn't go to 3 dimensions is that would require us to that would require a little more calculus than we're ready for. You have to use what's called multivariable calculus, and you'll learn all about that next quarter. We're just not quite ready for that yet. That's why they made it 2D. So in terms of real application, we're not quite there yet. But plus, this is silly. Can you imagine a density that was like this? So it's basically, as you're moving out, the density is changing from 2 to 8 in a cyclical way. Yeah, this is purely a mathematicians making up a problem that they think physicists would do that is not. So the joys of straddling the physics and math worlds. All right, so hopefully that at least is going to be good enough to help you do the other ones that are going to be kind of similar. I'm sure they have different shapes. But it's that same kind of idea, break it down, right? Break it down into the pieces. Okay, so then the next one on my list here is number 17. So let me hop down there, see what that guy looks like. All right, a bucket begins holding 20 kilograms of sand. The bucket is to be lifted to the top of a 10-meter tall building by a rope with density 0.1 kilograms. However, the bucket has a hole in it, oh nice, and leaks 0.1 kilograms of sand each meter it's lifted. So find the work done lifting the bucket and rope to the top of the building. All right, so I don't know who asked me about this one, but I like it. All right, so in terms of real world application, it could definitely be like this, where we have a leaky bucket of sand. But we're going to see if we can figure out what this thing, how much work is done. Okay, so let me finish writing this down. We got 10 meters and the rope is 0.1 kilograms per meter. Okay, I think I got all the information. If not, we'll come back to it. So let's go back to the whiteboard. Let's see if we can get this thing set up. So I'm going to go ahead and just clear this. We'll start new. All right, so here's our picture. We got the building. It's 10 meters tall. So we'll go ahead and write that. All right, hanging over the building here is a rope. That's going down, that's connected to the bucket. All right, so there's our bucket. And we're gonna lift this thing all the way up, and we want to figure out how much work is done. All right, so how do we calculate work? What's the process in general?
Fx dx integral.
Okay, so we're going to integrate our force times our displacement. Okay, so what I'm going to suggest we do is break this into two pieces. We look at the rope, and then we look at the bucket separately. Do you see why I want to do that?
Because it's leaking, and you also have to take into account the density and gravity.
Yeah, and it's really that first part, Susanna. Yeah, I want to look at the bucket just separately, because the bucket, it's the fact that it's losing mass makes it kind of weird.
Yeah, I broke it down into two, and then I still got it wrong, so I kept trying. But 18 was a similar question, and I did 18 right. I think I just set it up wrong somewhere.
Okay, well, let's see if we can take care of this. And I promise you're not the only one that probably has a question on how to deal with this guy. Okay, so let's think about the rope and the bucket separately. All right, so we'll even start with the bucket. Okay, so the bucket, its mass is changing as we go, right? And so if we look at the force on it, the force is going to be its mass times acceleration, so mass times gravity. The mass started out as 25, but we're losing 0.1 kilograms. Yeah, losing 0.1 kilograms every meter that we go. So we're going to lose minus 0.1x, and then we have to multiply that by 9.8. So that's the actual force due to gravity that's on that bucket. Okay, so then we need to do force times displacement. The displacement's the little dx chunk. And so the total work done for this then is going to be the integral from 0 to 10 of the 9.8 times 25 minus 0.1x times dx. So the first two parts here are the force. That's the weight of the bucket times the displacement. All right, so there's the piece for the bucket. We good? All right, so then let's do the rope. Sorry, I was trying to minimize some windows here. All right, so for the rope, let's think about this one. Again, its force is going to be, or its work is going to be force times displacement. But this one, what's nice is that we don't have to worry about the rope changing mass or anything. So let's look at it as just a little chunk of the rope. So let's just look at this little slice of the rope. In terms of how far it's going to move, it's going to have to move X. So when it comes to our work is force times displacement, the displacement is going to be X. All right, so then what's the mass of this little piece? Well, its mass is going to be the density we were told, 0.1 kilograms per meter. So 0.1 kilograms per meter times its length. Well, its length is a little tiny differential guy, which is going to be a dx. So that makes its force 9.8 times 0.1 dx. So then when we go to the work, it's going to be that force times displacement. So 0.98 dx times x. And we're going to make that go from 0 to 10. So I know you're used to having the dx on the back. I'm trying to keep it together just so that we can see that this is force times displacement. Just like here, we had force times displacement. So this is the other reason I wanted to break it into two pieces, is that how we build the work depends. It's a little bit different here. Like the differential chunks for the bucket was the differential distance it moved, where the rope, it was the differential chunk of rope, right? So it shows up in a different place. But we're just going to add those two together, and that'll get us our total work done. Anyway, so does that help, Susanna? Does it look better for you?
Yes, it does. Thank you.
Okay, awesome. All right. I have to find my list. What was I looking at next? Okay, so the next one, I guess, is going to be one of the ones from 20 to 22. Let's go see what those guys look like. All right, so let's just go find number, say, 21. All right, cool. So this is a fluid pressure. This is awesome. You guys, the ones you've asked about are all different examples, so I like it. Okay, so a trough, 7 feet long, 1 foot high. Vertical cross section of the trough parallel to its end is shaped like the graph of y equals x to the fourth from -1 to 1. The trough is full of water. Find the amount of work in foot-pounds, foot-pounds, required to empty the trough by pumping the water over the top. All right, and then I say note, use 62 pounds per cubic foot as the weight of the water. All right. Let me write all this garbage down. Y equals x to the fourth, -1 to 1, 7 feet long, 1 foot high. Okay. So let's see if we can figure this out. So this is another work problem. And so we're going to actually kind of approach it the same way, where we want to figure out the pieces that we're moving and get that force times that displacement. So let's draw another picture here. So first of all, what this thing looks like. All right, well, it said it's like y equals x to the fourth, which is like a tighter parabola. That's cross section. And then it goes out in 2 dimensions, 3 dimensions. Okay, so there's our trough. So we know some things about this. We know that it's 7 feet from one end to the other, and it is 1 foot tall. All right, so we're going to be pumping water out the top. So the way that we want to approach this is kind of the same way. Let's find a little differential chunk that's going to move the same distance. So I'm going to pick a height. I'm going to look at, say, right here. So let's think about all the water that's at this level. Okay, well, it's going to extend back in this direction. Right. So that's the little piece that's at the same height. What shape does that have? Can you visualize it? Like if you're looking at it down from the top, what shape would you see?
A rectangle.
Yeah, that's a rectangle. So here's our little chunk of water. It's 7 feet long. Okay, so this, let's just think that the left here is the front of the tank and the right is the back of the tank. So it's 7 feet long. How wide is it? Well, that changes. Depends where we are, right? Near the bottom, its width is virtually 0. And at the top, I think its width is 2. So it's going to change depending upon where we are, but we need to figure that out. Because think about what we want, right? If we want the work, what we're going to need to do is we're going to need to integrate force times displacement. Right? So integrate force times displacement. The force is going to be the density times the volume. And the volume is the area times the thickness. So this is what we need to figure out in order to set up our integral. We need to know the density, the cross-sectional area, the thickness, and how far it's moving. All right, so let's start putting all that stuff in. So things we know. The density. That's easy. That's going to be the, what they tell us, 62. I hate our system, by the way. I'm a huge fan of metric. One of these days, maybe one of these days in my lifetime, I'll see us go to metric. I don't think we will. All right, so there's our density. Now, the cross-sectional area. Well, the area is going to be 7 times whatever that question mark is. So I'm going to put the question mark there still that we need to fill that in. The thickness is going to be a, let's call it a dy. All right, so it's a little differential chunk in y. And so then the question is, what is the displacement? Well, to help us with that, let's put coordinates on here. I am going to put my coordinate axes right there because they gave us the equation of this thing. And that's in the standard kind of coordinate system. So I think that'll be a little bit easier. So we basically need to figure out then how far is this moving, right? What is that distance right there? Well, we're going to do that same trick as always, where if it's at a height of y, and it's going to go all the way up to 1, we're just going to subtract. And so our displacement is 1 minus y. That top layer doesn't move at all. As we move down, it moves further. So it's the 1 minus y. And then the bounds on the y go from 0 to 1, because they told us it was 1 foot thick. All right, so we're almost there. The only thing we got to figure out is that question mark. All right, well, that's where we're going to use the equation of that side. So we know that the equation of that thing, let me run this over here. The equation was given by y equals x to the fourth. And if we think about just one little piece of this, let's just look at this chunk right here, right? We need to know, if we know that x, then we know that our width is actually 2x. So I need to solve this thing for x. Well, that tells me x is the fourth root of y. So then the width is going to be 2 of those. And that's our question mark. All right, so let's get this all together then. So we're going to have the integral from 0 to 1, 62 times 7 times 2 fourth roots of y times 1 minus y times dy. And now that's all in terms of y. So we can go ahead and do this integral. Obviously, when you're going to do this integral, you want to change this fourth root of y into y to the 1/4. Distribute it through. You're just going to have power rule to do all of these numbers, the 62, 7, and 2. Those can all come out front. So I just kind of want to point out the method, the process that I'm modeling. Notice that every time we've done one of these, I've started with the definition of work, force times displacement. Then I start filling in what are those things. I start breaking them down, right? Like I got the force, it's density times volume. And that volume is area times thickness and so on. And I keep trying to break it down into smaller and smaller chunks until I get to the point where I can insert those values. Because if you just start talking about, well, what's the weight of that slice? Oh, there's so much in there. But if we can break it down into smaller things, I say, okay, well, what's the width of that slice? Oh, okay, I can do that. What's the density of it? Oh, I know that, right? So start with the big idea and then break it down into smaller and smaller pieces. All right, so hopefully that guy is good. All right, so I'm going to go look at the last one that was on my list, which is something from the, oh, not something, it's a specific one, 23. Let's go take a look at 23. Okay, so this one's actually very similar, but we'll go ahead and get it set up. So tank shaped like a cone, has 5 meter height and 1 meter base radius. It's placed so that the circular part is upward. All right, so it's an inverted cone. It's full of water. We have to pump it all out. Pump it out by a pipe that is always leveled at the surface of the water. Oh. Okay, so then we've got the cubic meter of water weighs 10,000 newtons, i.e. the density of the water is 10,000 newtons per cubic meter. Okay, so it's a little bit heavier than fresh water. How much work does it require to pump all the water out of the tank? Okay. So let's see if we can figure this one out. Now, this is actually very similar to what we just did. It's just this time our cross-sectional area isn't a rectangle. Our cross-sectional area is going to be a circle. So here's our tank. Ugh, that was ugly. Oh, thanks, Adam. Also wants us to keep the answer as units of pi. Cool. I don't know that I'm actually going to get that far, but that is good to know. All right, so we've got that guy, and then, yeah, I can definitely see how that messed you up if you're just going to go to the calculator to get a number. All right, so let's think about this little chunk right here, this little differential chunk that we're pulling out. And so we're going to follow the exact same process. The work is going to be the integral of force times displacement. So the force is going to be its weight. So it's going to be weight times displacement. So the weight is going to be the density times volume. And then the volume again, that's area times thickness. All right, so it's exactly the same setup as before. So let's think about what we know. We know the density was given as 10,000 newtons per cubic meter. All right, the area is going to be pi r squared. We'll figure out what that is in a second, but we know it's a circle. Its thickness is going to be a dy. And then the displacement, it's the same kind of story as before. We need to know how far is that going. All right, well, it depends how we want to set this thing up. I suggest we do it the same way as before, which is if we know that that total distance is 10, and we know that this thing is a distance of y up, then its displacement is 10 minus y. At least I think I remember that it was a 10-meter tall tank. And then in terms of the bounds, since the tank was full, we're going to have to remove it all the way from 0 to 10. All right, so that leaves us finding the R of that circle. Well, the R of that circle is going to be the X coordinate. So what I'd really like to be able to do is figure out what is the X coordinate right there. We'll even put on some axes here. Okay, well, that's great if the R is the X, but the problem is we need it in terms of Y. So that means we need the relationship between those, which means we need the equation of this line. All right, well, what I can tell you about that line is that it's y equals mx. You're not going to notice that there is no b there because the way I've got it set up, it's going through the origin. So I just need to find its slope. Well, I know how far it rises. Question is, do I know how far it goes over? And they did tell us that. I actually forget from our, hold on, I can find it. Oh, and I totally lied. The height is only 5 meters. Oh my gosh. Sorry about that. Hold on a second. These guys are 5 minus y integral from 0 to 5 because it was 5 meters. And they told us that it's got a radius of 1. All right, so its slope is rise over run, which is 5. So the equation of that guy is y equals 5x. Well, again, I wanted the x. That guy's y over 5. So we'll fire that in here for our r. Whew. And I think that leaves us finally with the integral from 0 to 5. 10,000 pi times y over 5 quantity squared times 5 minus y dy. All right, so that then is going to give us the total amount of work that we need to do. And if we go back and we look at that question, So it just said how much work, enter the exact value. I guess that'd be why they want it as a multiple of pi. But I'll tell you what, if you're doing this and you put in the decimal, that is the correct amount, even if it's looking for a multiple of pi, let me know and I'll go in and manually give you the point. This one, okay, so you guys know I straddle the math physics world. The mathematician in me loves exact answers. It loves multiples of pi. The scientist in me is like, yeah, but that's useless. And this is a science question, so I would definitely go to this one being, yeah, decimal approximation is fine. But I don't know exactly what the people that programmed this question are looking for as an answer. So like I said, if you are pretty sure you've got the right number, just let me know and I'll look at it. Anyway. All right, so are we feeling better about this stuff? He says with a hopeful thought in his mind.
I have a question really fast on that one.
Yeah.
The knot. So mine is my radius. Yours was a 1. Mine's a 5.
Okay.
Change the equation to the line. Was that 1? Is that why there was no b?
There was no b because it went through the origin.
Okay, so there's just 0.
Yeah, because then the y-intercept is 0.
Okay.
So I would recommend that since you're the master of your coordinate system, make it so that the tip of that cone is the origin, and then your line is always just going to be y equals mx. The slope will depend on the height and the radius of the cone, but then this way you don't have a b.
So you got your 5 from the height of the thing.
Correct.
So if mine was 9, mine would just be 9x.
If it was radius 1 and height 9, then yes. Because I'm just doing good old rise over run. Right? Remember for your slopes from way back in the day? And the rise is going to be the height of the tank, and the run is going to be the radius. So I guess technically it would be height divided by radius. So whatever those numbers happen to be, you can put them in. And so for mine, it was height 5, radius 1. That's why I had a slope of 5. All right, so cool. Ish. All right. Okay, well, with our amazing remaining, 20 minutes, I'm going to show you a little bit about how to find the centers of mass of objects, because that's the one thing that we still haven't dealt with yet. We've talked about center of mass using some points, so I'm going to hop up to the whiteboard real quick and give you a real quick review of moments and how we find center mass for point masses, and then go to an extended object. So I'll be right back. All right, so we were talking about center of mass last time, and we saw what we had to do was figure out how far a particle was away and multiply it by its mass and add them up, right? The old teeter-totter thing. But we need to extend this to 2 dimensions. So let me show you how we're going to do this. If we had, say, particles that are in the plane instead of just on an axis. All right, so here's a plane, and suppose I gave you 3 point masses. So we've got one of them here at -1, 1. And that one that's at -1, 1, let's say that its mass is 3. We're going to go metric, so 3 kilograms. All right, then there's another point that's out at 2 minus 1. And it's got a mass of 4. And then lastly, there's a point out here that's 3, 2. And its mass is 8. Okay, so different mass objects that are in different places. And we want to find the center of mass. All right, so when we did it in the x direction, when all we thought about was x direction, so suppose that all of these were just in line in the x direction, we saw that the way that we would find the center of mass, is we took the sum of the masses times their x coordinates, and then we divided by the total mass, right? So I'm going to put that as an x bar. The x coordinate is going to be given by this point. We may not have written it exactly like this, but this is the idea. All right, so that's actually easy enough for us to do here. If we wanted to calculate this real fast, it would be 3 times minus 1 plus 4 times 2 plus 8 times 3. And the total mass would be 3 plus 4 plus 8. So if you were to do those calculations, you end up getting, let's see here, 24, 32 minus 3 is 29. So this is 29/15. So if we were only concerned with the x direction, we'd see that the center of mass is at 29/15. So just about 2. Which was where this guy was. And so you can kind of think of it as this mass out on the left is balancing out the one on the right. And in terms of left and right, we're balanced right here. Okay, now we've also got a y direction. Well, here's the deal. For the y direction, you do exactly the same thing, except we're not concerned with x's now. We're concerned with y's. I mean, just sort of turn your perspective. You go, if I want to balance in this direction, I want to do exactly the same idea. And we're going to get that our y bar, well, that's going to be the sum of the m times y over the total mass. So it's exactly the same structure. Well, if we do that with the y coordinates, we get 3 times 1 plus 4 times minus 1 plus 8 times 2 over that 15 again. Run the numbers on that guy, you get 15/15 or 1. All right, so that tells us then that the center of mass is at 29/15 1, which is like right there. And so what it's really telling us is that that is the one point that sort of balances everything. You could treat that point as the location where all the mass is located. To a physicist, that's huge, because then we only have one point we have to worry about instead of 3. So extending to 2 dimensions doesn't really change much, because we just do the same thing twice. For the x's, we're looking at how far away are we from the y-axis. And for the y's, we're looking at how far are we from the x-axis. All right, so that's cool, nice and easy. But the question is, what do we do if we have something that's not just points? What if it's an extended object? Because in the real world, that's what we're going to be dealing with, right? When we send, the rover up to Mars, we'll get excited, it's landing tomorrow. When we send that rover up to Mars, it's not just a couple of points put together. It's this big extended object, and we still need to know where its center of mass is so that we can send it in the right direction and blah, blah, blah. All right, so let's extend this to an object that's a little bit more complicated. All right, but realize that what we're going to do is the same thing every time. So let me give you some other terminology that you're going to see in the book. So remember this whole mi, xi thing that we added up? What you're going to see there, if you look at the book, they're going to call that my. And what this stands for is the moment about the y-axis. It's its name. I have no idea why it's called a moment, but it's the moment about the y-axis, because we're concerned with how far are we from the y-axis. And then the one that was the MIYI, that is MX, which is the moment about the x-axis. Okay, so if you see those words, you see that, oh, they're talking about the moment. Sometimes they're called the first moment because there's actually a second moment as well. Anyway, if you see that, this means it's the moment. So then when it comes to the center of masses, you'll sometimes see them written like this. So x bar is my over the mass, and y bar is mx over the mass. I'm not going to ever write that, because I know for me personally, this is confusing. The x coordinate has to do with my, and the y coordinate is mx. And then the my, it's not even any y's that we're adding up, it's just x's. And oh my God, it just drives me crazy. So I immediately just go to the, if I'm finding the x coordinate, I look at the sum of the mx's. I want the y coordinate, I'm looking at the sum of the my. So I'm only putting this here so that when you get to it on the homework or something, you don't go, what the hell is this? You never showed us this. I showed it to you. It's useless. So we're going to do it another way. Anyway. All right. So this is our goal then, is to always get this form no matter what our shape happens to look like. All right. So what we're going to do is we're going to go to a two-dimensional shape, an extended object, but we're not going to be boring. We're not going to make it a rectangle or anything like that. We're going to make it so that one of its sides is curved. All right, so you're going to see the same generic picture that I've given you 100 billion times. But let's say this is our shape. We'll then have thing. All right. So we're going to see if we can find the center of mass of this object. So here's what we're going to do. We're going to do the same trick we've done 100 million times, which is let's slice this thing up into little tiny strips. Because finding the center of mass of that strip is going to be pretty easy. If we think about where the center of mass is going to be for that, it's going to literally be in the center. So it's half the distance. We are assuming that the density is constant here, which is not always a good assumption. When density gets weird, there's still ways of dealing with that. It's just we're not ready for it. So what we can do is we can actually treat this strip as if it's at that point right there. So the coordinates of this point, let's call it x coordinate xi, like we're used to. It's in the ith rectangle, but we'll just call that guy xi. So then where its height is, well, it's going to be 1/2 f of xi. So if f is the function that's giving us the top, f of xi is the height at that location, and then we cut it in two because we're at the midpoint. Okay, so that's the location of that little piece, which is good to know. because if we're going to do moments, we need to know where it is. But we also need to know its mass. So let's think about the mass of that little strip. The mass is going to be the density times the area. So let's just go with the density of rho. And the area of this strip is its height times its width. So its height is f of xi, and its width is delta xi. So that's the mass of that little piece. All right, so that's everything we need to know about that strip. We've got its mass, and we know where its center of mass is. And so with this, we can now get our coordinates for our center of mass. So think about the three things we need. We need those two moments, and we also need to know the total mass. So let's start there with the total mass. It's going to be the sum of all of the masses of these little strips. Well, since I've cut them down into tiny, 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 and an infinite number of them, that's going to be an integral. We're going to integrate from A to B. And we're going to integrate the individual masses. So if you want to know the mass of the object, we already saw this forever ago. It was probably a week and a half ago or something like that. We saw that we get mass by integrating density. Right? So this is going to be the mass of this object. And we're going to have to divide by that when we find our centers of mass. Okay, then we have our two moments. I am going to go ahead and just write them out like this so you can see. So my, this is the moment about the y-axis. So this is the one that involves the x-coordinates. So remember what we do is we take the mass times the x-coordinate. Well, I'm going to add them all up. It's going to be an integral. I'm going to take the mass, so rho times f of x dx times the x-coordinate, which is x. So the my is going to be integral of rho x times f of x. But notice that I'm building it exactly the same way we did before. This is mass times its distance away. It just turns into an integral because we're doing an infinite number of these pieces. So there's our my. So then let's go to mx. So this is going to be the one about the x-axis. So this is the one that's the y-coordinates. So I'm going to do the same thing where I need to take its mass. Okay, so mass is rho times f of x dx. But then I need to multiply by the y-coordinate. And the y-coordinate, we already saw, was half of the function. So 1/2 f of x. So again, just like before, this is mass times y. It just looks a little bit different. So we can put that all together. And we get the integral from a to b of 1/2 rho f of x squared dx. So all three of these pieces require integrals. We need an integral to get the total mass. We also need an integral to get the two moments. Help us find our centers. So it probably looks way more complicated than it actually is. It's not that bad. So let me show you an example. Let's take a shape and find its center of mass, where that shape is not obvious where the center of mass is going to be. So here's your example. I think it's the only one we're going to be able to do today. But let's look at this piece right here. Let's look at cosine. And let's look at the chunk of cosine that's between 0 and pi over 2. Okay, so this is y equals cosine of x, 0 to pi over 2. So you've seen that shape so many times. The question is, where is its center? Where is the center? Okay, so let's find these three things, and then we'll use them to find our center of mass. Okay, so we'll start with mass. It'll be the integral from 0 to pi over 2. Let's look at what we need. We need density times f of x. So our density we'll just assume as a constant rho, and then our function is cosine. All right, so the rho is constant, pull that out. We integrate cosine, we get sine. The sine at pi over 2 is 1. The cosine or sine at 0 is 0. So we just get density. We just get rho. So the mass of that thing is just rho. Well, that's cool. Whatever the density is, yeah, that's going to be its mass. Well, that was because the area of that thing is 1. All right, so there goes mass, so I can erase that. So now let's find mx and my. So my is going to be the integral from 0 to pi over 2 rho times x times f of x. Okay, so this one we're just going to take x times our function. All right, now this guy, we don't know how to integrate. We haven't learned yet, but the collective we. It is possible to integrate. We have to use this thing called integration by parts that I will teach you. I think we're going to talk about that next week. We're going to start learning some more techniques for integration. All right, so for this one, you're just going to have to kind of trust me. I hate doing that. But if you integrate this thing and plug in pi over 2 and 0, you get pi over 2 minus 1. And then the density is out there as well. All right, so at this point, you just have to trust me that this is going to work. But that gets our my. All right, so now let's do mx. So this one, mx, and the integral from 0 to pi over 2, 1/2 rho times the function squared. Okay, so that's just the formula for the mx. Again, you can pull out that 1/2 rho. We're integrating 0 to pi over 2 cosine squared. And looking at that one, you probably go, oof, we don't know how to integrate that one either. Except we can. Check this out. And for those of you who know me, you know why I just got a big grin. We're going to use identities. Oh, yes, I know what you're thinking. Oh, great, all that stuff that we learned back then that I've forgotten because I didn't think it mattered and we don't have to worry about it. Yeah. Okay, so check it out. Cosine of 2x, or cosine squared of x. there is an identity for that is 1/2 1 plus the cosine of 2x. You can just smile and nod, but it is one of the identities. But check it out. If we use that, this is now something we can integrate. We pull that 1/2 out, so we have 1/4 row. And now we're integrating 1 plus cosine of 2x. That you know how to integrate. The 1 becomes an x. The cosine becomes a sine of 2x. You have to do a u substitution on it. But that one we actually can do. But because I know nobody really cares, this ends up being rho times pi over 8 once you get your value. There's a reason that we tortured you with identities. They're going to come back in a big way. When we get to this section, there are going to be a couple sections that are big on trig integrals in terms of techniques. You will be reminded of all those identities. So I think Adam's worst nightmares are being coming to life. And he's probably not the only. All right, so here we go. Now that we have all these moments, let's find that center of mass. All right, so here we go. X bar. X bar is going to equal this guy, the my, rho times pi over 2 minus 1, divided by the mass, which was rho. So pi over 2 minus 1. It's around 0.57. All right, so there's the there's the x coordinate of the center of mass. And then the y coordinate is done similarly. So y bar, that's going to be this moment, rho times pi over 8, again divided by the mass, rho. So we get pi over 8. So the center of mass for this object is pi over 8, comma, or no, that's the y coordinate. All right, pi over 2 minus 1, comma, pi over 8. So this shape could be treated as one point right here. So notice that the density just doesn't matter. It's always going to cancel out if we have constant density. And because of that, there's also another name for this point. And I do want to mention this before we leave. So this is the center of mass. But it's also called the centroid. Yeah, but the centroid, this is if we have constant density. But we use centroids for other things, like you could find, say, the centroid of California. That would be the point that is geographically the center of California. So we'd call that the centroid. So if your density is constant, you'll sometimes see that term, centroid. All right, so you're starting to see now how we deal with an object that's not just a standard shape. We're going to do a couple more next time. We spent a little bit more time going over homework than normal, so we'll continue playing catch up. Because I want to show you what it changes when it's both the top and the bottom have different shapes. The formula gets a little bit uglier, but it's the same idea. So we'll do a few more of these to practice. And then we'll move on to some more stuff about logs and exponents. So that's my goal for next time. We also have a quiz because it's our usual Friday quiz day. And I think this quiz is just going to be over the physics section. I don't remember what number that is. Anybody remember? What was the one we just did? 2.5? Is that the one you guys are asking? Okay, thanks, Lexi. You just gave me that. All right, so we're gonna have a quiz on Friday on 2.5. So as usual, get in there at 8:30. It will be ready for you. Get it uploaded by 9:10, and 9:10 we'll be back in here doing more calculus. All right. So I hope you guys all had an awesome long week. That's probably one of the reasons why we had to do so many homework problems. Don't forget to get those done by midnight tonight. And other than that, I will see you all on Wednesday. All right. Have an awesome day.
Thank you, Bruce.